So today we're going through and we're going to actually talk about the reaction rates at equilibrium, as well as we're going to go through the Le Chatelier's principle. Okay, so we're going to do a couple things here. So the first thing we're going to go through is that equilibrium calculation. So this is today's worksheet. We're going to go through 3 of the problems together, just to give you guys a heads up, and then you'll have 2 more to do on your own. Okay, so the first thing we got to remember is what equilibrium means. So that means that at some point, the amount of reactants that are converting into products is the same as the amount of products that are moving back and turning into reactants. So they're the same amount on both sides. So they're moving at the same rate. That doesn't mean they have the same amount of concentration on each. It just means that their movement is the same going back and forth. The other thing we got to remember is how to calculate the equilibrium constant. The equilibrium constant is calculated by taking the concentrations of your products divided by your concentrations of your reactants. So if we're solving this one, we have K EQ is going to be the concentration of products over the concentration of your reactants. And there's one more thing we have to realize every time we're doing these problems, is that 2 types of reactants and products don't count. So anything that is a solid or a liquid does not count in your equilibrium constant, because the concentration doesn't change. So their concentration of a liquid and a concentration of a solid, they don't count because they don't change, because they're based off of the density, not based off of everything else. So this liquid in this problem is not going to count for our equilibrium constant. So when we're doing it, it just turns into a 1 if it doesn't count. So this one just turns into a 1. So when we write out our equilibrium constant here, our KEQ is equal to our products, and since our product got canceled, it's just equal to 1 on the top divided by the concentrations of our reactants. So our reactants are SO3, which is a gas. So the concentration of SO3 times the concentration of water as a gas. So this is how we're going to set up our equilibrium constant right here. Because the liquids don't count, we're going to turn that into a 1, and the gases do count, so those ones we do need the concentration. So now, all we have to do now, since we have the setup for our equilibrium constant, now all we need to do is value. So what we're going to do is take the values from up here. The concentration of SO3 is 0.4. And multiply it by the concentration of water, which is 0.480. And this will give us our our equilibrium constant value. And you should get something along the lines of 0.192. And there's no units for this one, so the units go away. And then we should have how many significant figures here?
3.
Perfect. So our answer for this one's going to be 0.192. Does that make sense to everybody? Does anybody have questions on that?
Nope.
Mm-mm.
All right. So now I'm going to make it just a little bit hard. Okay, so if we read this next problem, it says, at equilibrium, at 100 degrees Celsius, a 2-liter flask contains 0.075 moles of PCO3 0.05 moles of H2O, 0.75 moles of HCl, and 0.5 moles of POCl3. Calculate the equilibrium constant for this reaction. So, in order to do equilibrium constant, we have to find the concentrations. Do you guys remember how to find the concentration of a substance?
Molarity.
The molarity, perfect. So we have to find the molarity, which means we have to do what?
Moles over liters.
Moles over liters. Which means we have to take each of our moles, so the 0.075, the 0.05, the 0.75, and the 0.5, and we're going to divide them by the amount of the volume of our flask. So our flask is a volume of 2 liters. So we're going to take each of those values and divide them by 2. So we're finding the concentration of PCl3. We take 0.075 moles divided by the 2 liters. Do the same thing with water. Do the same thing with the hydrochloric acid. And then we're going to do the same thing with our POCl3. So once we do that, we can calculate each of our concentrations for each of the different substances in the reaction. So the first one, the PCl3, did anybody calculate that concentration?
.0375.
Perfect. Okay, what about the next one?
.025.
Wonderful. The third one?
.375.
And then the last one?
.25.
All right, so now that we have our concentration set up, now we can set up the expression for our equilibrium constant. So if we're going back over here, we're looking for KEQ, okay? So remember, it's products over the reactants. So let's look at our 2 products. So we're going to take the HCl. We're going to find the concentration of HCl. And then if you guys remember from the Ed puzzle from yesterday, they talked about the fact that the coefficients in front, they become exponents to the concentration. So the concentration of our hydrochloric acid is going to be squared. Because we have 2 moles of hydrochloric acid made during this reaction. We're then going to multiply it by the concentration of POCl3. And then divided by our reactants. So we take our concentrations of the 2 reactants on the bottom. Does anybody not like this expression?
Isn't PCl3 a solid?
Perfect. So PCl3 is a solid. So remember, solids and liquids don't count in our equilibrium expression. They cancel out, they turn into 1. So we're going to get rid of our PCl3. The only concentration on the bottom is just going to be our H2O. So now that we have our setup, we have our expression for our equilibrium constant, we can plug in our values for the equilibrium constant to solve. So we have KEQ equals the concentration of HCl, which we found the concentration of HCl to be 0.375. And this gets squared because, remember, we have 2 moles made of hydrochloric acid, so we square it to remind us that there's 2 moles made, times the concentration of POCO3, which is 0.25. And that gets divided by the concentration of H2O. So if we look over here, our concentration of H2O is going to be 0.025. So then we plug it all into our calculator. So we do 0.375 squared times 0.25 divided by 0.025, and we should get a value of what?
Isn't it like 1.40625?
Perfect. Okay, and now we have to use significant figures. So how many significant figures should we have here?
3.
Okay, so then we have our KEQ is equal to, we round to 3 sig figs, 1.41. Perfect. Any questions on number 1 or number 2 at this point?
No.
Nope.
All right, we're going to go through one or more of these just because number 3 is a little bit different than the other ones. Okay, so this time it says that the equilibrium constant, KEQ, is equal to 798 at 25 degrees Celsius. For the reaction, 2 SO2s plus oxygen makes 2 SO3s. In a particular mixture at equilibrium, the concentration of SO2 is equal to 4.2 molar solution, and the concentration of SO3 is 11 molar. Calculate the equilibrium concentration of oxygen in this mixture at 25 degrees Celsius. So the first thing we're going to do is write our equilibrium expression. So we're going to set up our equilibrium expression of KEQ equals. What should I put on the top of my equilibrium expression?
Product? Oh,
Yep.
wait, no. Yeah.
11.0.
So let's write out just the expression. So don't add numbers yet.
Products
So-
over reactants?
And so it's going to be our products. You were right the first time. And what is our product?
2 SO3.
So how do I write that in my concentration on an equilibrium expression?
SO3 to the power of 2.
Perfect. Because the molar means we square it here. The 2 moles means we square it there. All right. Then what goes on the bottom?
The reactants.
The reactants. So if I'm writing those out,
SO2 to the power of 2.
awesome.
Then O2.
And these get multiplied together. All right. So now our next step is to plug everything in that we know and leave the one that we don't know as a constant, as the concentration or as the constant KEQ. So do we know our equilibrium? Do we know our equilibrium constant KEQ?
Yes.
Yes. What is it?
798.
798. Perfect. Do we know the concentration of SO3?
Yeah.
What is it?
11.
4.20.
Careful. So SO3 is going to be 11. Do we know the concentration of SO2?
4.20.
Yes.
4.2. Do we know the concentration of oxygen?
No.
No. All right. So the first thing that we could do here, there's multiple ways to start this, but the first thing I would say we do is multiply the concentrate by the concentration of oxygen to both sides. So we're going to take this and multiply it by O2. And we'll multiply it by O2. That way, the concentrations of oxygens cancel out over here, and we've moved it over to the other side. So now we have 798 times the concentration of oxygen on one side. And then we can do 11 squared. What's 11 squared?
121.
22.
21.
121 divided by 4.20 squared.
16.4.
Not quite, not quite.
$17.64.
28.8. What?
I'm hearing different numbers.
121 divided by 4.2.
Careful,
28 point.
Careful, this one, don't forget that
Oh.
4.2 is also squared. All right? So now we can solve that. There's 121 divided by 17.64. Did anybody get an answer?
6.859.
All right, and then our last step is to get the concentration of oxygen by itself. So that way we're going to divide by 798.
Point 0085.
So 0.009.
Careful, how many significant figures do we need?
Um,
How many?
2.
3, right?
We need 3 significant figures.
Oh,
Yep.
So
0.009.
remember, these 2 zeros don't count.
Oh, okay.
Alright.
So if we have 3 sig figs, what's it going to be?
0.0085. No, well, 0.000.
0.86.
There we go. This 0 counts because it's added after. So it counts because I put it in there even though the number exists without that 0. So that 0 counts. These zeros do not count. And then we have units for this one because it's a concentration. What are the units going to be?
Liters.
Molarity.
Molarity, or the moles over liters. Perfect. Are there any questions on this?
No, sir.
All right. So you guys have 2 more of those problems to work on, but we're going to go over one more thing. So we're going to go over that Le Chatelier's principle. Okay. So there's this table that I asked you guys to look at as well, and there was a video from YouTube that went over a problem and talked about Le Chatelier's principle. But we're going to go over what this really means. Okay. So we're going to use the same equation that they had in their the video that we could have watched. But Le Chatelier's principle just says that if there's a change in something, that there has to be a shift in concentration somewhere. So the first one that we can talk about is if I took this right here, if I took N2 and I added more nitrogen to my reaction. So I increased the amount of nitrogen that I have. If we were at equilibrium, we want that equilibrium to stay the same, which means that if I increase the amount of reactant I have, my reaction is going to shift or move to the right. And it talks about that up here. So if I increase the reaction of a substance, remembering that our equilibrium constant wants to stay the same. So our KEQ wants to be the same value. So if I change the concentration of my reactant, it's going to push everything the opposite way. So if I change the amount of N2 or nitrogen that I have, I'm going to push my reaction to favor my product side.
And the
Because it
same
wants
thing
to-
goes for hydrogen, right?
The same thing goes for hydrogen. If I switched it and I changed the amount of hydrogen that I had, so if I increase this one, it's going to push that reaction to go towards the product side because it wants to use up that hydrogen to keep that equilibrium constant the same, to balance out the equilibrium constant. Which means if I increase the amount of one reactant, what's going to happen to my other reactant here? What's going to happen to my nitrogen? Do we think that's going to also increase, or should that decrease?
Mm,
Increase.
So that one's actually a little bit trickier. So it's actually going to decrease because remember, if we added more hydrogen and the reaction then shifts towards the products. So now I'm making more ammonia. So then it shifts that towards the product. So it's making more ammonia afterwards. That means the amount of nitrogen, more nitrogen is getting used up. So this actually decreases. So if you increase the reactant, the other reactant that's being used up is going to decrease because it's getting more of that nitrogen gets used up to make that ammonia at the end. Does that make sense?
yeah.
All right. So that's just about concentration. So there's other things that we can change if we want this reaction to shift one way or the other. So they talked about the concentration, the increase of a concentration. It flips if we decrease the amount of a reactant or we decrease the amount of a product, it's going to shift towards that product. So if I take my hydrogen and I take away hydrogen gas here, my reaction is going to shift towards my reactants to then balance out the opposite way. So if we make more of it, it pushes it towards the opposite direction. If we take away some, it's going to pull that reaction towards the side that we removed concentration from. All right. And then there's a couple more things that we can talk about. Pressure. So pressure and volume are going to be related. Okay. So pressure and volume are related. Okay. So pressure and volume are related because they're going to shift toward the side that has less moles. So if we look at this reaction here, which side has less moles, the reactants or the products?
The product.
The products have less moles.
Wait.
Because this has 2 moles, and you're right, because this has 4 moles. So this one has more moles. So now if I take it in terms of volume, if I give you a lot of space, do you think they're going to have more particles flying around or less particles?
More.
There's going to be more particles. So the higher the volume means more particles. So it favors, in this reaction, which side would it favor? The reactants or the products?
The reactants.
The reactants, because there's more moles or more particles flying around. And if there's more room for those particles to fly around, there's going to be more of them there. So it favors the side with more moles. So it favors more moles. So whichever side has more moles, it's going to favor. Then it's the opposite with less volume. So less volume means that there's less room for these particles to fly around, which means that which side would it favor? The side with more particles or the side with less particles?
Side with less.
With the side with less particles. So it favors less particles, which means that it's going to favor less moles. All right. And I said that pressure and volume were related because if we think about it, if you are in a smaller container, so if I have a container and I make less volume, I'm pushing down to create a smaller space. If I'm pushing down to make that smaller space, I'm creating more pressure every time there's less volume. So less volume is the same as saying that there's more pressure. Okay, so less volume is the same as saying there's more pressure. So if there's more volume, if I've given you more space, so I went from a small space to a larger space, the pressure is going to be smaller, which means that there's more particles flying around as well. Okay, so there's a smaller amount of pressure if there's a larger volume. If we give more volume, there's a larger amount of pressure present. Does that make sense?
Yeah.
Yeah?
Yeah.
Okay. The last couple things I talked about is temperature. Temperature is determined based on if it's an exothermic reaction or an endothermic reaction. So if it's an exothermic reaction, is the heat, are we going to have heat on the reactant side or the product side? So is heat entering the system or is it exiting the system?
It's exiting.
Perfect. Exothermic means that it's going to leave the system, which means that if I increase the amount of heat, so if I increase the amount of heat, it's going to move. So the heat, if I said this was an exothermic reaction, heat would be over here. Because it's exothermic, heat is being released. It then is considered just like our reactants and our products. So if I increase this, it's going to push the reaction away from where the heat is. So if I increase my heat, my reaction moves the opposite direction. So if it's exothermic, my heat is on the product side, which means that if I increase it, I'm going to push towards the reactant side. It's going to push and shift towards the reactants. Oppositely, if I decrease it, it's going to go towards my reactants, which means that if I decrease, or towards my products, so if I decrease my heat in an exothermic reaction, it's going to pull the reaction towards the products because it wants to increase that heat again, keep that heat the same. And then it's the same thing for the opposite way. So if we had an endothermic reaction, so heat was on the reactant side, and I increased it, it would push the opposite direction. So if I increase the heat, it would move towards the products. And if I decrease the heat, it will pull towards the reactants again. So endothermic and exothermic, the heat is being pushed towards or away from where the heat is based on if you're increasing it, it's going to go the opposite way. If you decrease the amount of heat, it pulls it the same way. Does that one make sense?
So it's always going to the left?
So it's not always going to the left. It's going to the left if you have an endothermic reaction and you decrease the amount of heat. So
And if you increase it, it's going to go to the right.
yep, endothermic, increase heat, it's going to go towards products. Because the heat is on the reactant side. If you decrease the heat, it's going to go towards the reactants. And then these are going to flip for exothermic. So I'm just going to copy and paste real quick. So these are going to flip for our exothermic. Exothermic, if you decrease the heat, it's going to move towards the products. And if you increase the heat, it's going to go towards the reactants. Because in an exothermic reaction, our heat is being released, so it's on that product side. So going towards the products means that there's less heat being added to the system, or it's cooling down. If it's going towards the reactants, that means that there's more heat than needed, so it's pushing that towards the products again. Any questions there?
No, sir.
All right. And then our last one they talked about is a catalyst. Remember, a catalyst doesn't get used up. It shows up before the in the reactant side, and it shows up in the product side. So if I had a catalyst here,
Nothing would happen.
nothing happens because it's on both sides. So even if I increase the amount of catalyst I have, it just changes how fast that reaction moves into equilibrium. It doesn't change the equilibrium constant itself, because these go away. So they don't change the equilibrium itself. So they won't affect if you have more or less. Are there any questions about this or about the other part of our lesson today?
No.
No? All right, guys, that's all I had for you today.